Okay, so I'm just going to make a really brief introduction video about exponential functions for you guys. Okay, exponential functions. So what is an exponential function? That's kind of the first question to address. So a typical exponential function in the sort of simplest form looks something like this. F of x equals b to the x, okay? B is called the base, okay? B is called the base of the exponential function. And there are some conditions on the base. Remember when we were looking at polynomial functions, the coefficients could be basically anything. B is a lot more restricted, okay? So B has to be greater than 0, okay? And B also can't equal 1, okay? Now, there's a reason for this. The reason that b has to be greater than 0 is so that whatever function we get winds up being continuous, okay? So if we think of, if b were, say, -1, then anytime you had a square root or an even-powered root as your exponent, the function would suddenly be undefined, okay? So you'd have a bunch of disconnected points. The idea here with b not equaling 1 is if you had 1 to the x power, that would just be 1 no matter what value you pick for x. So it would be a straight line. So that's more like a constant function. It's not really a different type of function. So b has to be greater than 0 and b can't be 1. Now there are different things that happen if you have different types of bases. So let's look, for instance, at what happens if you have an exponential function like, say, 2 to the x power. What does the graph look like? Let's try to make a sketch. Well, the first thing we could do is maybe plug in 0. So 2 to the 0 power, that's just 1. Then maybe we'd plug 1 in. Okay, 2 to the first power is 2. Then maybe we'd try 2. 2 squared is 4. Okay, then maybe we'd try 3. 2 to the third power is 8. Then we might be wondering what happens if you go left on the x-axis. So let's say it's -1. Okay, so remember 2 to the -1 is the same as 1 over 2 to the 1, or 1/2. Okay, then maybe we'd try -2, so 1 over 2 to the 2, okay, or 1 over 4, so 1/4. As we go back, 1/8, and so on. Okay, so the overall shape of this thing is something kind of like that. Okay, and we can talk about its end behavior just like we talk about polynomial end behavior. Okay, so we can see as x goes to -infinity, f of x goes to 0. And as x goes to positive infinity, f of x also goes to positive infinity. Okay? What happens if, let's say, we change things around and we have 1/2 to the x power? What does this graph look like? Well, kind of the opposite, right? If we had 0, okay, we'd still be here at 1. But then at 1, we'd be down at 1/2. At 2, we'd be at 1/4. And at 3, we'd be at 1/8. Okay? Then maybe we'll trace back. So at -1, we'll wind up swapping this. So we'll be up at 2. At -2, again, we're going to wind up swapping this. The numerator and the denominator will wind up at 4. And you can probably see the pattern at -3 will be at 8. Okay, so essentially, we wind up with a mirror image of our first graph. Okay, so the end behavior of this is as x goes to -infinity, f of x goes to infinity, and as x goes to infinity, f of x now goes to 0. Okay, so the end behavior is swapped, just like the image itself that you get is swapped. So we can kind of separate our exponential functions, our basic exponential functions, into two main categories. There's exponential growth functions like this, where you can see it grows as x gets larger, and exponential decay functions, where y gets smaller as x gets larger. Okay, so it all depends on the base. So if the base is greater than 1, you have growth. Okay, if the base is between 0 and 1, okay, you have decay. Okay, that's all for now, just some basic terminology and graphs of the exponential functions, and I'll be posting more this week.